Good evening, everyone. Good evening. This is Rashmi greeting you, and welcome to Unacademy's online YouTube classes. And this is Rashmi. I have been teaching you about alcohols, phenols, and ethers. We have completed preparations of alcohols, phenols, and ethers. We have also already started reactions of alcohols and phenols. And phenols, alcohols reactions over. Phenols, we are in halfway through. We stopped at coal-based reaction, if you remember. So today we'll start with coal-based and Rimer-Tiemann, two important name reactions. Okay, yes. So once again, welcome all of you to Unacademy's YouTube live session. Before we start with the class, okay, let me tell you a little more about Unacademy Plus classes and special classes. I'm also teaching in Unacademy special classes, okay, so free classes, even you're free, and the link will be sent in Telegram channels. So please join Telegram so that you get the link so you can come, join the classes. Unacademy, if you want to have a comprehensive batch, that is physics, chemistry, mathematics, biology, and physics, chemistry, biology. If you want a comprehensive batch, live classes where complete syllabus preparation will be done. So, okay, you have to subscribe to Unacademy Plus. Students, Unacademy Plus class is the best for Karnataka CET aspirants, those who are going to write exam in 2021 and future years. Okay, those who are writing CET exams, this is the best class. What are the highlights of Unacademy Plus? Okay, you will get premium content in affordable price. Now, what do you mean by affordable price? You can subscribe to Unacademy Plus for 12 months, 6 months, even for a 1 month. If you are subscribed for 12 months, you have to pay 12,375 rupees. That amounts to only 1,031 rupees per month. Or you can go for a 6-month plan by paying 10,125 rupees. That amounts to only 1,688 rupees per month. Or you can go for a trial period of 1 month by paying 2,250 rupees. This is only for new subscribers. Okay, yes. Now students, if you use my referral code Rashmi2020, you are not even paying this much because you will get 10% reduction. By using my referral code, you will get reduction. So you will get a good plan, okay, which well structured plan for an affordable price, dedicated live doubt clearing sessions, quizzes at regular intervals, test series, daily practice problems, full length mock tests, all is available in Unacademy Plus. Okay, best of all is with a single subscription, you have unlimited access to Unacademy Plus classes, all the live streaming classes, all the recorded classes available during your subscription time. You can access and you can prepare. Okay, so if you're interested, go for subscription. Not only you, your friends, your neighbors, relatives, those are not unaware of it. Okay, tell them what you know, spread the word so that more students benefit from it. Okay, yes. So once again, welcoming you to Unacademy, live YouTube classes, and let's start the class. Now first is coal-based reaction. Okay, we were learning about reactions of phenol, electrophilic aromatic substitution reactions, electrophilic aromatic substitution reactions. Nitration, halogenation, we have already finished studying in two different conditions, nitration, halogenation. Okay, we have already finished studying. So third one is coal-based reaction. Now what is coal-based reaction? Phenoxide ion, see, phenol is converted into phenoxide ion. What is phenoxide ion? Phenoxide ion is this, O minus ion. Okay, phenoxide ion. Since it's O minus, Na plus will get attracted to O minus, so you get sodium phenoxide ion. This is sodium phenoxide. Sodium phenoxide or sodium phenate, or sodium phenate is also called as. So phenoxide ion is generated when phenol is treated with the sodium hydroxide. Okay, phenoxide ion, okay, A minus Na plus. So phenoxide ion is generated when phenol is treated with sodium hydroxide. Okay, why phenoxide ion is generated before you treat with before you actually carry out the reaction? Because phenoxide ion is more active towards electrophilic aromatic substitution reaction than phenol. Phenoxide ion is more active towards electrophilic aromatic substitution reaction than phenol. That is why phenol is first come to into phenoxide ion. Okay, see, phenoxide ion will undergo electrophilic substitution reaction even with the weak electrophile like carbon dioxide. Okay, so now phenoxide ion undergo electrophilic substitution reaction with carbon dioxide at 413 Kelvin at 6 to 7 atmospheric pressure to give you salicylic acid. See, more explicitly, if I have to show the reaction is like this. See, phenol. Okay, phenol reacts with sodium hydroxide to give you phenoxide ion. Okay, sodium phenoxide ion, which is treated with the carbon dioxide, which is heated with the carbon dioxide at 413 Kelvin. See, temperature has to be 413. If above this temperature, you will not get ortho-substituted product. See, with respect to OH and COH, OH is your functional group. Okay, sorry, COH is your functional group, OH is substituent. So COH, this is the carbon, first carbon. So with respect to this ortho position. Okay, so if you want ortho substitution, you have to maintain 413 temperature. If the temperature goes above 413, OH will be at the para position. So you get para substituted product. So para substituted products are predominated products. Okay, so if you want ortho substituted product, temperature has to be maintained at 413 Kelvin. So phenoxide ion is heated with carbon dioxide at 6 to 7 atmosphere. You get sodium salicylate. Sodium salicylate on acidification with the concentrated HCl. Okay, you acidify with concentrated hydrochloric acid. You will get salicylic acid, or also called as ortho-hydroxybenzoic acid, or 2-hydroxybenzoic acid. 2-hydroxy. This is IUPAC name. Benzoic acid. When you write ortho, that is common name. So these two are common names. Okay, salicylic acid. See, if they are OH and COH in the ortho positions like this, 1, 2 positions. Okay, ortho positions. Then this is called salicylic acid, or ortho. See, ortho-hydroxybenzoic acid, or 2-hydroxybenzoic acid. So salicylic acid is the product. So coal-based reaction. This is coal-based reaction. So once again, let's go through. So phenol is treated with sodium hydroxide. So sodium phenoxide ion is formed, which on heated to 413 Kelvin with the carbon dioxide at 6 to 7 atmosphere. Sodium salicylate is formed. Which on treatment with acidification with HCl will give you salicylic acid. Now, you might be wondering, ONA becomes OH and COH should have been produced, is it not? Because in the textbook, if you see reaction, that is how it is given. Okay, they directly give you OH and COH. This is not shown. They directly show you from here. Directly here only they will write. See, in the previous equation, you see directly here only step 1 and 2 written here together they write. But actually, you will get CONA, sodium salicylate is formed. So when you have OH and COH, OH phenolic hydroxide group and carboxylic acid group. Carboxylic acid is more acidic than phenolic OH group. That is why COH becomes CONA, not OH. Okay, CONA. Okay, COH becomes CONA, which on acidification will give you COH, salicylic acid. This is coal-based reaction. I hope you understood. Okay, next reaction is Riemer-Tiemann reaction. Students, if you have any question, you can post it there. So I will be checking it. Okay, if you have questions. Yes, I hope if any questions are there, you can post it there so I can answer you. Okay. Yes. Okay. As I was telling you, next is Riemer-Tiemann reaction. Okay. No chat though thus far, so I think you have understood. Okay, Riemer-Tiemann reaction. Riemer-Tiemann reaction means what is question will come. What is Riemer-Tiemann reaction? Same way, what is coal-based reaction? Also question will come. What is Riemer-Tiemann reaction? On treating phenol with the chloroform and sodium hydroxide in the presence of sodium hydroxide. Treating phenol with the chloroform, CHCl is chloroform. Treatment of phenol with the chloroform in the presence of sodium hydroxide. CHO group, see, CHO group is introduced at the ortho position of the benzene ring with respect to OH to the ortho position. CHO group and aldehyde group is introduced to the ortho position. Okay, this is called as Riemer-Tiemann reaction. So on treating phenol with the chloroform in the presence of sodium hydroxide, a CHO group, that is aldehyde group, is introduced at ortho position of phenol. Okay, ortho position of the benzene ring. This reaction is called as Riemer-Tiemann reaction. Okay, now exactly what happens in the Riemer-Tiemann reaction? Phenol is treated with sodium hydroxide and chloroform. Okay, you will get an intermediate called as benzyl chloride. This is the intermediate benzyl chloride, which continues reacting with sodium hydroxide. Okay, further treatment with alkali. You will get sodium salt of benzaldehyde or sodium salt of salicylaldehyde. Okay, sodium salt of salicylaldehyde, which on acidification ONA becomes OH. sodium salt of salicylaldehyde. So between OH and CH, OH is more acidic. So ONA, okay, ONA and CH will be there. That is called sodium salt of salicylaldehyde. Which on treatment with the acid HCl, you will get salicylaldehyde. Now exactly how the reaction takes place, okay, this is the reaction. This is how the reaction takes place. See, phenol first reacts with NaOH, so sodium phenoxide is formed because phenoxide is more reactive. So you get phenoxide ion. Phenoxide ion is then treated with the chloroform, okay, reacts with the chloroform from the ortho position with respect to ONA. From the ortho position, hydrogen will come out, and from chloroform Cl. So HCl is the byproduct. So what is remaining from chloroform? CHCl2 gets added to the ortho position. So CHCl2. This is benzyl chloride intermediate. Benzyl chloride. This is the intermediate you get, benzyl chloride. So from ortho position, okay, with respect to O minus, ortho position hydrogen and Cl from chloroform will come out as HCl. So what is remaining part of chloroform? CHCl2 is added to the ortho position. So you get benzyl chloride plus HCl as the byproduct. Benzyl chloride thus formed continues to react with alkali. So NaCl is removed. So 2 alkyl, because there are 2 chlorine atoms, is it not? So 2 sodium hydroxide you take. So you get 2 NaCl as the byproduct. So OH, in the place of Cl, OH gets substituted. So CHCl2 becomes CHOH twice. Now CHOH twice, next I have written like this, okay, OH like this. Within the molecule, okay, CHOH twice within the molecule, water molecule is eliminated, okay, water molecule is eliminated. So if water molecule is removed, what is remaining? CHO, you get aldehydic. So aldehydic group is introduced at the ortho position. Now what is remaining? Just ONA has to be converted into OH. So OH is converted into ONA by treating with the base. So ONA is converted into OH by treating with an acid. So ONA is converted into OH. So NaCl byproduct. See, Cl from acid and Na from the ONA. Okay, you will get NaCl as the byproduct, and you get salicylaldehyde. Salicylaldehyde. Salicylaldehyde is the product. So coal-based reaction, salicylic acid is the product, okay, and Bremer-Timmer reaction, salicylaldehyde is the product. So this is very, 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 very important reactions. I hope you understood. Any doubt? Any doubt thus far? These 2 reactions. Any doubt, students? I hope you understood. Okay. Next is reaction of phenol with zinc dust, powdered zinc dust. You heat phenol with zinc dust. Okay, you heat phenol with zinc dust. What do you get? You get benzene. Benzene is the product, and zinc oxide is the byproduct. So when phenol is heated with zinc dust, benzene is the product. So in hydrocarbons chapter, under benzene concept, you will be learning. This is the one of the methods of preparation of benzene. Treatment of phenol or heating phenol with zinc dust. You get benzene. Okay, one of the method of preparation of benzene. So this is now under phenol, we are learning this as reactions of phenol. So phenol, when heated with zinc dust, benzene is the product, and zinc oxide is the byproduct. Okay, so reaction of phenol with zinc dust. This is another reaction. Another important reaction is oxidation. Oxidation. Phenols undergo oxidation with the chromic acid. What is chromic acid? H2CrO4 is the chromic acid, and chromic acid is produced in situ within the reaction mixture. Chromic acid on its own is not stable. So within the reaction mixture, it is produced by the reaction between sodium dichromate and sulfuric acid. Sodium dichromate, you know potassium dichromate, K2Cr2O7. Now instead of potassium, you have sodium, that's all. Or potassium dichromate or sodium dichromate reacts with the sulfuric acid. So okay, when they react, you get chromic acid. Chromic acid now acts on phenol. The chromic acid thus formed reacts with the phenol to give you a compound called as benzoquinone. Benzoquinone is a conjugated, see, double bond, single bond, double bond, single. It's a conjugated diketone, C double bond O, C double bond O twice. So it's a conjugated diketone. Benzoquinone is a conjugated diketone. Conjugated diketone. It's a colored compound. Okay, conjugated diketone. It's a colored compound. It's a dark brown color. See, this happens even when phenol, when it's a pure and okay, freshly prepared, it is colorless. But when it's kept for a longer time in shelves, it gets oxidized even by the atmospheric air. So phenols slowly converted into mixture of quinones, okay, and this quinones will give them dark brown color. So when long preserved phenol, you see they have a tinge of brown color because of the formation of quinones, okay, benzoquinone and other quinones which are dark brownish color, okay, which will impart color to phenol. So this is oxidation. So phenol undergo oxidation in the presence of the chromic acid to give you benzoquinone. Oxidation of phenol with the chromic acid. How does chromic acid prepared? In situ by the reaction of potassium or sodium dichromate with sulfuric acid. Okay, the chromic acid reacts, oxidizes phenol to give you benzoquinone, a conjugated diketone. Okay, yes. So phenols, even in the presence of air, when slowly undergo oxidation to give dark colored mixture of which contains mixture of quinones. Okay, mixture of phenol and quinones. I hope you understood this. Any doubt? Okay, here completes the reactions of phenols. Okay, here completes reactions of phenols. Reactions of phenols over. I hope you understood this. Okay, reactions of phenol done. Okay, now let's go to ethers. Okay, ethers. Let's start with preparations of ethers. Preparations of ethers. We have learned ethers nomenclature, classification, nomenclature. We have learned. Now we are starting with preparations of ether, and first method of preparation of ether is dehydration of alcohol. This is one of the reactions of alcohol. When alcohols are dehydrated to 443 Kelvin, you get alkene, is it not? Now by dehydration of alcohol, you can also prepare ethers. See, look at this. Ethanol. Okay, ethanol. When you dehydrate using concentrated sulfuric acid, dehydration can be done by using protic acids like concentrated sulfuric acid, phosphoric acid. You can use concentrated sulfuric acid, phosphoric acid. Okay, you can use any one of these acids. But if you use concentrated sulfuric acid and the temperature is 443 Kelvin, ethanol is converted into ethene. This is what you have learned. Okay, under the reactions of alcohol, you have learned conversion of ethanol to ethene with the mechanism. The temperature is very, very important. I have said there also. If it is 443 Kelvin, you will get a phenol. You will get alkene. At the 443 Kelvin, you get alkene. Correct? Now, if the temperature falls below 443, that is, let's say if it is 413 Kelvin, instead of alkene, you will get the ether. Ether is the product. Ether will be the product. I hope you understood. Any doubt? Any doubt? Any doubt, students? Okay, no doubt. Okay, let's then go continue. So as I was telling you, if you dehydrate ethanol with a protic acid like sulfuric acid and phosphoric acid at 413 Kelvin, you get ether. You get ether. So ethanol, when dehydrated 413 Kelvin, you get 413 Kelvin, ethanol will give you diethyl ether or ethoxyethane. Diethyl ether or ethoxyethane. Okay, if it is 443, ethene. Okay, ethoxyethane. Let's learn the mechanism. How is ether is formed when at 413 Kelvin. At 413 Kelvin, how do you get ether? So again, 3 steps. Okay, first step is same as your preparation of alkene, from ethanol to alkene at 443 Kelvin. First step was what? Protonation of ethyl alcohol. First step is same. Okay, sulfuric acid H2SO4 is basic acid. It will release H plus and HSO4 minus ions. So H plus ion from acid gets taken up by lone pair of electron of oxygen. Oxygen has 2 lone pair of electrons. It will be taken up by lone pair of electron of oxygen, and you get protonated alcohol. See, protonated alcohol. Now oxygen has 3 bonds around it. So you get a plus charge. So you get protonated alcohol. Once protonated alcohol is formed, second step onwards it is different. First step is same. In preparation of ethene, in second step elimination of water molecule takes place. You get a carbocation. Here what happens is elimination of water molecule takes place. So carbon gets a positive charge. But the second molecule of alcohol at 413 Kelvin, second molecule of alcohol, oxygen has lone pair of electron. That lone pair of electron attack this carbocation. So you will get like this. You will get see. Lone pair of electron will take up the carbocation. So you get dialkyl attached to oxygen like this. Again, oxygen has plus charge because 3 bonds around it. Okay. Now, just to eliminate the proton, you will get required ether. Diethyl ether. Okay. Now, let me write and show you. So, this is what happens. Mechanism. Okay. Mechanism of conversion of ethanol. C2H5OH. Okay. 2 molecules in fact. In the presence of sulfuric acid. in the presence of sulfuric acid, which acts as a catalyst at 413 Kelvin, you are getting C2H5O C2H5. So ethanol to diethyl ether or ethoxyethane. So first step is, sulfuric acid will release H plus ion and HSO4 minus ion. Now H plus ion will attack CH3. Let me write ethyl alcohol as HTOH like this. Okay, it will be taken up by the lone pair of electron of oxygen. So first step is protonation of alcohol. So you get protonated alcohol, CH3, CH2O already has a H, another H added to it. So lone pair of electron used. So oxygen gets plus charge. And oxygen cannot remain as plus charge because it is attached to hydrogen and carbon, and oxygen is more electronegative. So it will pull the electron from carbon, and oxygen will pull the electron. So next step, next molecule and a second molecule of alcohol, H like this. Oxygen has two lone pair of electron, plus when water goes, you have carbocation H2O. It will come out as water molecule. So you have water molecule as the byproduct, plus the carbon becomes positively charged. So the lone pair of electron attack the carbon. Okay, you will get CH3, positively charged carbon, carbocation is attacked. Okay, CH2, CH3. And oxygen already has an hydrogen. So now three bonds around it. One pair is used to form bond with the carbon, okay, which is positively charged, carbocation. So one electron is lost to carbon. So oxygen gets positively charged. And this is the second step. In the third step, okay, you take the product of first step, that is CH3, CH2O, CH2, CH3 plus oxygen plus charge. Now if you want ether, you just have to eliminate proton. Just eliminate proton. H plus will come out. So whatever was used in the first step, it will be given back. So this will go and attack second molecule. So this goes on. So you will get major product CH3, CH2O, CH2, CH3. That is ethoxyethane. Ethoxyethane. That is the IUPAC name. Or you have diethyl ether. Diethyl ether. See, two alkyl groups, same alkyl groups. So diethyl ether will be the name. I hope you understood. So this is the mechanism of conversion of ethanol to diethyl ether at 413 Kelvin in the presence of protic as a catalyst like or acid like, or you can also call it as dehydrating agent. Is it not? They are dehydrating agent. Okay. So alcohols undergo dehydration because dehydration by dehydration of alcohol is the name heading you have learned. By dehydration of alcohol, preparation of ether by dehydration of alcohol. That is what you have learned. Okay, so the dehydrating agents are protic acid like sulfuric acid, phosphoric acid. These are the dehydrating agents. So the product formed will be ether if the temperature is 413 Kelvin. I hope you understood. So this is the first method of preparation. The second method of preparation is very, very important. Williamson's synthesis. It's also called as Williamson's ether synthesis or simply Williamson's synthesis. And in this reaction, alkyl halide reacts with sodium alkoxide. Sodium alkoxide. When oxygen and alkyl group where oxygen carries negative charge, sodium will be there because it is negative positive attraction. Is it not? Sodium alkoxide. So sodium alkoxide. So reaction between alkyl halide and sodium alkoxide gives ether. Now it will give ether if the alkyl halide you have taken is primary. Alkyl halide has to be primary because the nucleophile here is alkoxide ion. Okay, alkoxide ion should attack the positive charged carbon. How come carbon becomes positive charge? So look, alkyl halide is attached to halogens. Halogens are more electronegative than carbon. So the electron will be pulled towards halogen. So it is like the negative charge. This is the positively charged. Okay. So when nucleophile, that is alkoxide, and approach this molecule, this bond is now completely broken. Simultaneously, a bond is formed between oxygen and R. So between RO minus, okay, lone pair of electron plus RX. See, this bond is formed. This bond is formed. This bond is broken. Okay. Now this is a single step reaction. In the single step reaction where two reactants are there, alkoxide and your nucleophile and alkyl halide. So follow second order kinetics. So the mechanism is SN2 mechanism. And you already know from haloalkanes chapter, if the mechanism is an SN2, what is the reactivity of alkyl halide? Primary, secondary, tertiary. primary alkyl halide is more prone towards SN2 mechanism than secondary than tertiary. So alkyl halide has to be primary. Okay, that is one reason. Second reason I was telling you, see, if you look at nucleophile has to attack this carbon. Now, if smaller the alkyl group, simple the alkyl group, then primary alkyl group is best. If it is secondary and tertiary, the nucleophile cannot reach carbon. See, if it is secondary like this, okay, secondary alkyl halide is there, or if it's tertiary alkyl halide, so this is tertiary alkyl halide. So this carbon is secondary, this carbon is tertiary, is there. Nucleophile difficult to attack this carbon because of the steric hindrance. Alkyl groups are there, 2 alkyl groups in secondary, 3 alkyl groups in tertiary. Okay, nucleophile cannot attack this positively charged carbon because of the steric hindrance provided by the R groups, bulkier groups. Carbon, the positively charged electrophilic carbon. Okay, electrophilic carbon. The carbon is called electrophilic. Why? Because it is attached to halogen. So carbon develops partial positive charge. This is partial negative charge. So partial positive charge means what? It is electron deficient. So the electron deficient species are electrophilic. So electrophilic carbon has to be attacked by the nucleophile, is it not? But if more R groups are surrounding it, instead of hydrogen, in the case of primary alcohol, these are hydrogen, or one R group, rest is hydrogen. Whereas in secondary and tertiary, more alkyl groups. Because of steric hindrance, nucleophile cannot reach that carbon. That is one reason. Second reason, with respect to primary, see, primary is RCH2OH. Okay, so this carbon, okay, is attached to only one electron donating R groups. R groups are electron donating in nature. Whereas in secondary, CHOH. Okay, CHOH. Let me delete this. Okay, secondary is a CHOH. Okay, CHOH, where there are 2 R groups. Third, tertiary is a COH, which has 3 R groups. So here 2 R group electron donating groups, here 3 electron donating groups. So when you move from primary to secondary to tertiary, the electrophilicity of the carbon, that electron deficiency of carbon is decreasing, because here carbon only 1 R group is providing electrons. Here 2 R groups are donating electrons to positively charged carbon. Here 3 alkyl groups are providing electrons to positively charged carbon. So the positive charge on the carbon from primary to tertiary decreases, because when you move from primary to tertiary, more and more R groups are there. So these are called electronic reason. Second is electronic reason. First is steric reason. As your R group increases, nucleophile cannot attack this carbon. Second, this carbon's positive charge decreases when you move from primary to tertiary, because greater number of R group, more electron is donated to the carbon. Okay, so whatever electron is losing to, okay, it should be OX. Whatever electron it is losing to halogen, okay, is provided by the R groups. So the electrophilicity of this carbon is decreasing because of the plus sign. R is providing electrons because of inductive effect. Okay, so that is why primary alkyl halide is best. So alkyl halide has to be primary. Now sodium alkoxide, and this can be primary, secondary or tertiary. It can be primary, secondary or tertiary. You will get like this, see, NaX come out. So you just add R in the place of Na. You write R, that's all. So you get ROR. See, like this. RX plus, if I write NaOR like this. Okay. NaOX is removed. So you have ROR. So ether is formed. And salt is the byproduct. Salt will be byproduct. See, for example, see, this is primary alkyl halide. Ethyl bromide is a primary alkyl halide. See, CH3, CH2, Br. Primary alkyl halide. The carbon to which Br is attached, internal attachment only one carbon atom. So primary. Okay, primary. Okay, reacts with the primary sodium alkoxide. So NaBr you remove. So in the place of Na, you will write in alkyl group. See, C2H5O, C2H5 of diethyl ether. Okay, diethyl ether. Okay, another example. That was both were primary. Now here alkyl halide is still primary, whereas your sodium alkoxide is tertiary. See, the carbon to which oxide is attached, attached to 3 other carbon atoms. So tertiary. And okay, tertiary butoxide, called as tertiary butoxide. Tertiary butoxide. Okay, yeah, sodium tertiary butoxide treated with the methyl bromide. So what happens? NaBr you remove. Okay, in the place of Na, CH3, right? So you get CH3OC like this. Or in the place of Br, CH3Br. Okay, nucleophile is replaced by another nucleophile. Okay, another nucleophile, that is this nucleophile. So you have, so in the presence of CH3 thrice CONA minus plus, Br is replaced by CH3. Okay, OCCH3 like this. Okay, so in the place of Br you have tertiary butoxide. That's all. That's all you have to remember. Alkyl halide, halide you remove, nucleophile from the alkoxide. Nucleophile is the alkoxide ion. You write the alkoxide ion, whichever. Don't write Na, remaining everything you write. Remember, oxygen has to form bond with the carbon. Oxygen, because oxygen and sodium bond, ionic bond here is broken. And carbon and Br, which carbon and Br bond is broken, that carbon will get bonded with oxygen. You get the ether. You will get ether NaBr. Now, what happens if you take instead of primary alkyl halide? What if happens if you take tertiary alkyl halide? Okay, this we will discuss in Williamson's ether synthesis. I told you again and again, alkyl halide has to be has to be primary. Now, what if you take tertiary? Will be discussed, and more preparations and reactions will be discussed in the next class. Okay, so time's up, students. Thank you for being a wonderful audience. I hope you understood. Keep studying, keep attending the class, and better yourself. And those who are out there who are celebrating Christmas, and happy Christmas to you. Okay, Merry Christmas. Enjoy the day, and also be safe and keep studying. Goodbye, students.